Hello students, welcome to today's lecture. Today we are going to learn the equation of continuity. Actually, we'll derive the equation of continuity. Okay. Earlier we discussed momentum shell balance. Okay. So earlier, what was the problem in momentum shell balance? We have a specific problem, and according to that, we do the momentum shell balance. But the problems we have studied so far was very simple, so it was very easy to derive the velocity shear stress profile using momentum shell balance. But however, if we have complicated problems, then it will be difficult by using momentum shell balance. Okay, so that's why we want to derive in general equations. So the general equation which can be applied to any problem, okay, in any coordinate system. Okay, in this chapter, we are going to derive the equation of continuity, equation of motion in rectangular coordinates. However, you can use the equation of continuity and equation of motion in cylindrical or spherical coordinates, which is given at the in the appendix, right? So I will give you the PDF. So we'll derive it in rectangular coordinates. But if you want to learn, you can try deriving in cylindrical or spherical coordinates. Okay. So so first we will derive the equation of continuity. Equation of continuity is nothing but it's a mass balance. Okay. So we have general formula, right? Accumulation is equal to mass in minus mass out. Okay. Only the terms will be like here it will be kg per hour, kg per hour. Okay, it's like mass flow rate. Fine. So on the left and right hand side, the units will be in mass per unit time. Okay. So let's derive it. Okay, so you have to consider a control volume, small element. Okay, this is dv, or you can say delta v. Okay, so my coordinate system is like this: x, y. It is right hand thumb rule, so x cross y should give you z. So it is giving in the thumb direction, right thumb direction. So it is fine. Okay, so this will be your delta x. This will be your delta y. We are considering very small volume element. Okay, and we are going to use this to calculate for the whole fluid. So this is how it's done, and in this direction we have delta z. So what is the total volume? Total volume, that is small volume, delta v, is delta x, delta y, delta z. Okay, let's say fluid is entering in this x direction, this surface, right? So it is coming in, going out. Fluid is coming in this phase and going out. Fluid is coming in this phase in the z direction and going out. Okay, you can also see here in this diagram, you can see coming in, coming out at x plus delta x. Okay, similarly, if you take y direction, this phase and this phase, so it is coming in here and going out at this phase. It is going in z direction, this place, and going out in this direction. Okay, so we have total of 6 phases, means one phase for coming in, one phase for going out. So you will have total in minus out, three pairs, right? 2 phases are reserved for one direction, so we have 3 in and out pairs. Okay, also you have to use, so definitely you can write m dot, right? But since you're dealing with fluids, we are not dealing with solids, so this will be meaningless. So why don't you express this in terms of the properties of fluid, that is density. So fluid, the most important property is density in fluid mechanics. So what will be mass flow rate? So it is nothing but, so generally rho velocity, density into velocity is nothing but mass flux. Okay, if you multiply it with area, then it is mass flow rate. So it will be unit kg per hour or mass per unit time. Okay, we will be using this formula to the balance. Okay, so we have, so this is the general accumulation is equal to in minus out, right? So it is given rate of increase of mass, that is accumulation. Rate of mass in, rate means it should be kg per hour. Okay, similarly rate of mass out, kg per hour. Okay, so okay, we'll do it now. So what is the accumulation? Accumulation is nothing but dm by dt, right? Okay, so what is mass? Mass nothing, mass is nothing but, then can you write this mass in terms of density, that is your volume, volume into density, right? So what is the volume of this small element we have taken here? You already know, delta x, delta y, delta g, because we are using rectangular coordinates. Okay, so instead of m we are going to write rho. Okay, rho v by dt. Okay, this should be dou, because the velocity is function in 3 directions. So, and the density can be also a function of time and space. Okay, so now your coordinate system or your volume is delta x, delta y. These are not changing with time. So you can remove this volume out of this because it is not changing with your time. So you can delta x, delta y, delta z. This is the volume, dou rho by dou t. So this is nothing but accumulation. Okay, so remember this, keep it aside. So you can see here. Okay, so this is your accumulation. Now we'll come to the right hand side. Okay, so what is the mass flux? Let's do in, then we'll multiply the area. So what is the mass flux in this phase? So rho, what is the, it is in x direction, right? So rho vx, we have to calculate. This is calculated at which phase? At x. This is in, right? This is mass flux. What is the mass flux out? So this is rho vx only, but calculated at x plus delta x phase. Okay, this is mass flux, but we are doing here mass flow rate, right? Kg per hour. So you have to multiply with area. So what is the area here on this phase? So what is the area of this? I think this is nothing but delta y, delta g, right? Delta y, delta g. The same for here also. Delta y, delta g. Right? So this is the mass flux in x direction. Similarly, you can write what is the mass flux in y direction? Rho vy, y minus rho by at the other phase, that is y plus delta y phase. Similarly, you have to add on. Okay. Similarly, in z direction, rho vz at the phase z, this is the z phase. rho v z, this is mass flux at z plus delta z, this phase. Okay, so I've done mass flux in and out in all the three directions. That is your, total mass in minus out. So definitely this is mass flux. So you have to multiply it area. So both have same, both faces. This face has same area, and that is equal to. So that is equal to what? So for in y direction, so this is your, sorry, this is y direction. Okay, this face. So what is the area? Delta x, delta z. So delta x, delta g. Okay. The same for the face at this y plus delta y. Similarly, in z direction, this is the z direction. So what is the area of this face? This is nothing but delta x, delta y. So we have to multiply delta x, delta y, right? All three you have to add together. This is on the right side in minus out. Okay. So if you put this here, you can see they've got the same, right? Okay. Now, as earlier in shell balance, what we did, we multiplied, right, on both sides by some this delta x, delta y, delta g. Then we take limits, right? So similarly, in this formula, multiply both sides by delta x, delta y, delta g. So what you will get? You will get dou rho by dou t equal to rho Vx at x phase minus rho Vx at x plus delta x by delta x, right? Similarly, you'll get rho Vy at y phase minus rho Vy at y plus delta y divided by delta y. And one more term, here is this one, to make some rho. Okay, I will go down. So I will get one more term, that is rho v z at z surface minus rho v z z plus delta z, right? Delta y divided by delta z. Okay, so you'll get this. Now just take limits. So if you take limits delta x tends to 0, limit delta y tends to 0, limit delta g tends to 0, right? So what you'll get? What you'll get here? You'll get dou rho Vx by dou x, right? You'll get minus. Why? What is the definition of, derivatives? Okay, derivatives you take like f at x plus delta x minus f x by delta x, right? So if the limit delta x tends to 0, then we have df by dx, right? See, this x plus delta x term is in the front, right? But here x plus delta x term is on the back. So if you rearrange this, so minus will, right? You can rearrange it. So minus, if you take out the minus, then you will get rho vx at x plus delta x minus rho vx at x, right? So that's why here it is minus. Similarly, this will give you minus dou rho vy by dou y. Similarly here minus dou rho vz by dou z, right? So if you collect all the terms now, I will erase. So you'll get dou rho by dou t equal to minus dou rho v x by dou x. Okay, I will take out minus common plus dou rho v y dou y plus dou rho v z by dou z. Okay. Okay, so what is this? Can you replace it with something? So I already told you, right? This Nabla operator. So this is this is vector. If you take the divergence of let's say any function, so f, so it is nothing but definitely this has to be vector. Okay, let's take v vector here. So divergence of v, it is nothing but dou vx by dou x plus dou v y dou y plus dou v0, right? So similarly, you can directly apply here. So if you use this formula, so you can replace this with this nabla dot rho d velocity vector. Okay, so this is your continuity equation. Okay, so you might ask, see, density, why density is a function of time? It could have been 0, right? So actually density can change with time or with distance. So density can be a function x, y, z, and t, right? So then here, if density is a function of time, that means there is accumulation, right? Okay, because we are using density to denote mass, so it can be a function of time. But if there is no accumulation, you can directly strike out to 0. In the earlier momentum shell balance, we did not use this accumulation term. That's why it was put 0. But here we are deriving the general equation. Okay, so the general equation is this. You can simplify this general equation according to the problem, right? So you can see here. So this is your general equation of continuity. Okay, you can apply to any problem in rectangular coordinates. I will show you the equation of continuity in the other coordinates once we finish this. Okay, so this is the equation of continuity, or equation of, you can say, mass balance. Okay, so I will tell you a special case. What if the density is constant? Okay, it doesn't change with time or any distance. That means density constant means it is not a function of x, y, z. Okay, definitely this it will be function of time if there is a accumulation. Okay, we have to ignore that. Anyway, it will zero. So it's, let's say density is not function of the position. So this is called, then it is rho is constant, or we can say it is incompressible fluid. Incompressible fluid. You cannot compress that fluid. Okay? So density is constant. So if density is constant, what happens to this equation? So this simply reduces to rho by t equal to minus rho v, right? So now you can take the density out of this equation because it's no more function of x, y, z. Also, this term will go 0. Okay, so it is not a function of time as well. Okay, so what will happen now? So that means this is true. So divergence of the velocity vector is 0. So remember this. This is also continuity equation for incompressible fluid. You can say this is the equation of continuity for incompressible fluid. If it is not, if it's compressible, then you have to use this equation. But however, if the density is constant, you can use directly this equation. Okay, this is the continuity equation. Okay, so in exam, one might ask if the fluid flowing through a pipe has a profile something like this, some values are there, let's say some x square I cap minus y square j cap, right? So that this fluid is incompressible. If somebody asks you to prove that the fluid is incompressible, then you have to show that the divergence of velocity vector is zero. The velocity vector will be given, just take the divergence. If after doing the math, if you get zero, that means the fluid is incompressible or the density is constant. Okay. So thank you. In the next class, we will study the equation of motion.